excess heat measurement in cold fusion experiments suffer from credibility because of tenuous connection with radiation. But if you remember, there's another byproduct expected, which is helium. And our speaker today is the leader of the group, which has claimed to measure helium and get good correlation with excess heat. So as you'll see, the amounts involved are small. So when you start to measure small things, it's very difficult. So his results are controversial. So to get a flavor of the controversy, last year, well, when I called Dr. Miles to ask to invite him, he was reluctant to come. He said last year gave a seminar at Brigham Young, and they kept him for 3 hours. Subsequently, published a criticism and sent it all over the world. And so then when he found out about that, he published his rebuttal and sent it all over the world. So if you want to see those, Susan Isles has copies of those for students who are interested in this matter. Anyway, he's here to tell us about his work, and if I can get the right piece of paper here, tell you a little bit about his background. He received a PhD from the University of Utah in 1966, was then NATO postdoctoral fellow, and he's had appointments as professor of chemistry, Middle Tennessee State University, September 69 to September 78. And since 78, I think he's been at the Naval Weapons Center in China Lake, California as a research chemist. He has a number of honors. For example, Sigma Xi Award, Best Scientific Paper at NWC in 1985 and 1988 both. So, without any further ado, Dr. Melvin Miles.
I'd like to thank Professor Dash and the Portland State University for this opportunity to speak. I was told I need to put this microphone on if I can figure that out. Okay, great. Since we made this regraph, our name has changed. We were the Naval Weapons Center, but January 1st we became, in the consolidation program, we're now the Naval Air Warfare Center, and so it's hard to keep track of these name changes. What I'm going to talk about today is our excess heat measurements correlated with helium measurements, and we did this work in collaboration with the University of Texas. Ben Bush, who was a postdoctoral student there at the time, was the main person involved there. Also Professor Legowski, you may recall, if you're in chemistry, he's editor of the Journal of Chemical Education, if you see or know that journal. Before I forget, there are 2 books on cold fusion. This has a positive slant in favor of something really existing. This is from Eugene Maloff, who was at the time a science writer for MIT. He's now left that post due to the controversy, partly. And if you want to read a book with a negative slant, Too Hot to Handle by Frank Close. These are both, I think they're both good books to read if you have the time and interest to look into them. And so that don't forget later on, these are some reprints of our paper on helium and excess heat, and also reprints on our calorimetric papers. So after the seminar, anybody that's interested. Go back through time just briefly. We know the announcement came in March 1989 about Fleischmann and Pons reported fusion at room temperature. People all over the world rushed into laboratories to duplicate these claims. I was in the laboratory that Saturday myself, and soon there's also skepticism. People were not finding it, and it's not an easy experiment as they thought. And in fact, in my case, I worked 5 months before I found anything positive. The headlines continued through April 1989. Some people were reporting energy gain, like in Texas, but at MIT and major laboratories like Caltech, they were getting negative results. Stanford had some positive results. So it was rather a mixed bag. There were some positive reports, some negative reports. Now, just a little review on fusion. There is a huge energy barrier that you have to overcome somehow, the Coulombic energy barrier, in order for fusion to take place. It's such a large barrier that you really don't go over the barrier. You tunnel through it by a process called quantum mechanical tunneling in order to get to the product. Normal fusion, at least hot fusion, goes by two pathways. You either toss out a neutron and form helium-3, or you throw out a proton and get tritium. That's the normal hot fusion pathways. If you analyze the barrier, to simplify it, I've made it a square barrier. The probability of tunneling through the barrier from quantum mechanics is this equation right here. The main thing to note here, there's a lot of constants here, but the width of the barrier, A is the width of the barrier. So how close those particles get together has a big effect on whether or not tunneling can take place. For example, at ordinary atomic dimensions, 1 angstrom, your probability of tunneling is 10 to the minus 76,000. Well, that's about 0, I think you would agree. But if you get to within 10 to the minus 15 meters, nuclear dimensions, more or less, then you do have a probability of tunneling through the barrier. This just shows that you do not go over the barrier, no matter if you, even at very high temperatures, 100 million degrees Kelvin, your chance of going over the barrier is still quite small. So I think everybody pretty well agrees that fusion has to take place by a tunneling process. How does electrochemistry come into this process? Well, electrochemistry really can produce tremendous effects at surfaces of the electrode. For example, when you electrolyze heavy water, you split the molecule apart. If you relied on temperature alone to do that, you'd require very high temperatures before you'd break that molecule apart, but you can do it quite easily with a voltage. And if you use the Gibbs free energy relationship and calculate for an overvoltage of 0.8 volts, which is not unusual, easy to attain in electrochemistry, you can show that in effect equivalent to an effective pressure of 10 to the 26 atmospheres of pressure. So as far as the electrode is concerned, when it has 0.8 of a volt overvoltage, it's behaving as if it had that higher pressure. The original paper by Fleischmann Pons used this figure. That's where I got it. But it's not real pressure. It's effective pressure. It's like activity in solution. The right word for it would be fugacity in the gas phase. It's really a fugacity. But it is a tremendous driving force that drives the deuterons into the palladium. And when these deuterons enter the palladium, they first form an alpha phase, but that quickly then go on to the beta phase. And normally you can load the palladium up to about 0.6 of hydrogen per palladium if you're working with hydrogen. The lattice changes, the lattice expands, becomes more like an alloy and becomes a semiconductor. So there's quite a few changes goes on as you load up the palladium. Now, a lot of people claim that unless you get the loading up above 0.8, that is 0.8 atoms of deuterium per atom of palladium, you would not expect anything to happen. Their experiments, like Stanford Research Institute, where they had that fatal explosion not too long ago, that's what they claim. You'd have to get the loading at least up to 0.8, and preferably up to about 1 to 1. If you get about 1 deuterium per palladium before you really expect any major effects. Now, how does helium enter into this? Under normal hot fusion, you do go either the one pathway to form tritium or the other pathway to form helium-3. But in a metal lattice, is that necessarily true? Does that necessarily apply? And This was from a newspaper account in Los Angeles Times, actually, where they were early on hypothesizing that in the lattice, perhaps this very energetic helium-4, rather than getting rid of its energy by throwing out a neutron or a proton, gives up its energy to the metal lattice. And by giving up its energy to the metal lattice, it becomes stabilized and stays as helium-4. And this is one of the early theories that were put forth. Well, whether you're talking about a chemical reaction or a fusion reaction, you have to show that there is some product. If you have a chemical reaction, you have to expect a product. If you have a fusion reaction, you've got to expect a product there. So the major criticism of cold fusion for the first year and even continuing on today is, where is the product? If you have fusion, what is the end result? Where's the nuclear debris? And this is what we were aiming for in our work. Perhaps it was helium-3 or helium-4. And that's what we try to focus on, to see if we see any isotope of helium present. And to prove this, especially to prove it's helium-4, you have to have control experiments and make sure no air gets in, flush everything out thoroughly. You have to determine what your detection limit for helium is, and run experiments in water instead of heavy water to see whether any helium occurs there. If it's coming in from the air, you would get the helium in the light water as well as the heavy water. And this is a difficult problem to detect the helium, because you have tremendous amounts of deuterium gas coming out and oxygen gas coming out, and you're trying to look at helium in the presence of these gases coming off at a concentration of about 1 part per billion. And that's not an easy problem. In fact, if you have 1 watt of excess power in a fusion reaction, you can do a calculation. It would take you 73,000 years to produce 1 mole of helium. That is 4 grams of helium. 1 watt of power for 73,000 years to get 4 grams of helium. So it's not an easy problem to find the helium that you would expect. Again, the hot fusion pathway, tritium, or else helium-3 and neutrons, but these products were not being found in experiments. Some tritium was being found, but not nearly enough to explain the heat. There was some evidence of neutrons, but much lower than you would expect. And so it did not seem that this new process, whatever it was undergoing the conventional hot fusion pathway. So people came out with other theories. Professor Swinger, Nobel Prize laureate, proposed maybe it goes to helium-3. And if it goes to helium-3, you wouldn't get any other type of radiation except maybe heat. Or perhaps it goes directly to helium-4, like we just showed a few minutes ago. And then heat, you wouldn't have anything else to find except the heat and the helium-4. Or perhaps it involves lithium-6. You can also get fusion from deuterium and lithium-6 that goes to helium-4, with the only product being heat. And so you would not see the neutrons or tritium in that case. Well, as I mentioned, we worked 5 months from March until September before we found any evidence at all for any excess heat. This shows our early calorimetric designs. We did it different ways. Here we have the thermometer right inside the cell. That leads to some problems when you measure the temperature directly in the cell and compare it to the temperature outside the cell, because as the electrolyte level drops, air is always a better insulator, or gas is a better insulator than liquid, and so your cell constant would change. So that was a problem. We then went to a cell design where we put the thermometer outside the cell, but right next to the cell, and compared the temperature there with the temperature in the bath outside the cell. And that seemed to work better. It wasn't so sensitive to the electrolyte level changing within the cell. We had this outside compartment filled with water, regular water, just to keep everything in thermal equilibrium. But nevertheless, even with this design, we did not see excess heat. We were getting about exactly the same amount of heat out that we put in. And one reason for this, there's a lot of mistakes that we made, a lot of mistakes that other people made that people don't realize. If you're trying to load the palladium up with deuterium, for example, if you have palladium above the solution level, then of course you drive the deuterium down in the solution, but you have no electric field above the solution, so it has an easy pathway to find its way back out. So you can never have any palladium exposed above the solution. That's one mistake that we made early on, and I think a lot of other people made. Furthermore, you have to keep the electric field symmetric about the palladium. If you have wide gaps between the counter-electrode coil, like shown here, you have spaces in between where the electric field is weak, and therefore the deuterium tends to escape out of those weak field areas rather than staying in the palladium. So that was another error, that you have to keep the symmetry very good about the palladium and keep the electric field uniform if you're going to load it up with the deuterium. This is the design that we went to in September 1989 that we finally got excess heat. Now you see we have a short piece of palladium. It's about a 1/4 inch diameter. This one's the larger pieces anybody was using at that time, 0.635 centimeters diameter. And we only made it about a 1.1 centimeters long, so it's rather a short piece. We coiled the counter-electrode quite symmetrically around it. And so we had the palladium sitting inside the coil, and the coil was fairly uniform. We kept it as uniform as possible about the palladium. When we went to this design, then after 6 to 8 days, we started seeing excess heat. It took about that long to load up and get the deuterium fully loaded with the palladium. But after 6 or 8 days, we started seeing excess heat effects that were as large as 30% more heat coming out than we were putting in. The way you measure excess heat is by Newton's law of cooling. The heat out is equal to a constant called your cell constant multiplied by the temperature difference inside the cell, or close to the cell is the way we did it, close to the cell, and minus the temperature of the bath that the cell is sitting in. That's the heat coming out. That's the heat. In our particular cell, our cell was designed so that the heat would escape by conduction. Fleischmann-Pond cell was a Duraflash. Their heat was mostly escaped by radiation. So ours is somewhat different, as the heat flow is by conduction rather than radiation. But your joule heat in is your electrical power you put in, your voltage, minus 1.53 volts, and some people argue with that, but that's the voltage it takes to split the heavy water into deuterium and oxygen, and you can combine that and get that energy back out. So as long as you don't have the gases recombining, you're justified in subtracting 1.53 volts. In fact, even in Frank Close's book, The Critic, he will agree to that. If you do have recombination, then you have to compensate that for how much recombination you have going on. But it's been pretty well established that as long as your electrodes are fully submerged in the solution, you do not have recombination taking place. People look for it, we've looked for it, and it does not actually occur unless your electrode is exposed to the gases in the space above the electrolyte. Then it could be a problem. What we calculate then is the heat out, measured from the calorimetric cell constant and the temperature difference inside the cell and outside the cell, divided by the heat in, the voltage minus 1.53 times the current in amps. That's the joule heat in. Now, to establish that we could do good calorimetry, we also calibrated the cell several ways. One way was by joule heating, where in place of the palladium we put in a 20 ohm resistor, and we apply different powers to the resistor, put in different powers here, and get different delta T's, difference in temperatures measured inside the cell and outside the cell. This shows results both in heavy water. The squares down here are experiments in heavy water. And then about 6 months later, we came and extended this graph, but this time we used light water. You can see, even though we did this in 2 different experiments, one in heavy water and one 6 months later in light water, there is effectively no difference. They're all on the same line. It's the same line, and that shows you 2 things. One, that the heavy water, as far as the calibration goes, the heavy water, light water calibrates about the same. And the second thing is there's no change in the cell coefficient over time period as long as 6 months, because the 6 months of data fits in with the earlier data. You may also note that it doesn't go exactly through 0, and that's the point to bring up, because the reason for that is that the cell is not completely submerged in the bath. Some of the cell is exposed to the air in the room, and therefore some of the heat does escape out into the room. We didn't submerge it because we didn't want any danger of water from the bath getting into our cell and contaminating it, so we always had the top a little bit above the bath level. I don't have time to go through a lot of mathematics here, but you can break this up into two terms. One is the heat going into the bath, one is the heat going out the top, and you can use a cell constant for the bath, a cell constant for the top, and go through some algebraic expressions and show that you still get a linear relationship. As long as you keep the bath temperature constant and the room temperature constant, it'll still be a linear relationship. But the intercept will not go through zero. In fact, from the intercept you can calculate, put the power equal to 0 here, and you can calculate what T2 is, and T2 then will be somewhere in between the bath temperature and the room temperature. And you can also calculate what amount of the heat flow is into the bath and what amount is through the top. And you get these two constants here. But you see that roughly 6/7 of the heat flow is into the bath, 1/7 of the heat flow is out the top. But you still do calorimetry as long as you keep the room temperature and the bath temperature fairly constant. This shows measurements of the cell constant. And this is important because some people claim that these cell constants may change with time, but these are different experiments over almost a 2-year period. But you see, even with joule heating fits in with other calibrations. The way we do other calibrations is that we would calibrate the first few days of electrolysis when you would not expect excess heat, and then you can do a calibration during that period. So you can do the calibration while you're doing electrolysis as long as you don't have excess heat, or you can do the calibration by joule heating where you know you don't have excess heat. And anyway, you see that there's pretty good agreement. And these are different experiments. The cell is not exactly the same every time, so you wouldn't expect the constant to be exactly the same. The way we insulate the top is not exactly the same, for example, in each experiment, but it's close. And you can see the standard deviation is about 2% from one experiment to the other, but it shows the constants are all, in various experiments, come out pretty much the same. Okay, our focus then is to measure the excess heat and try to correlate it with measurements of helium in the gases coming out of the cell. And the way we would do this, we have the electrolysis cell here. We're not showing the calorimetry part of it, but just the electrolysis cell. We do electrolysis, the gases go up out the top, and they flow through this slink flask, the 500 milliliter volumetric volume round bottom flask is what it is, with the inlet and outlet and the stopcocks. And then it goes through an oil bubbler because you want to keep it always under positive pressure so there's no air that can get in. And then it goes from the oil bubbler out into the atmosphere. You have to be very careful not to get any air in the process. You have to flush out all the lines to boil off nitrogen. That's why these inlet ports are for, is to flush out all portions of the line. Even any little piece of glass tubing that's exposed, you have to flush that out carefully. You can also back flush through the cell by putting a needle down through here and using that as a one-way valve. You can flush the cell out. But we always did all these precautions. But in addition, doing electrolysis, this flask is generating enough gas to flush it out every 73 minutes. So this flask is being flushed out 19 times a day by the electrolysis gases that are flowing. So it is self-flushing. It's always flushing itself out to 19 times a day. And we would never disconnect it until it was on at least 2 days. So it always had an opportunity for at least to be self-flushing 38 times before we disconnected. This shows some of the calorimetric measurements during this experiment. One here, and this line here, is where you exactly break even, where the heat we're getting out is exactly equal to the heat coming in. We didn't start this until about the 12th day because we don't normally get excess heat until you run it for a while. And furthermore, we were working out problems with the possible leaks in the system. But you see on the 12th day, we were getting excess heat, at least in cell B. The dark line is cell B. We always ran 2 cells side by side, the same current going through both cells. One was called cell A, one called cell B. Cell A was not generating excess heat at that time. This is where we took a gas sample. Here's the example then of a D2O electrolysis with no significant excess heat. This is an experimental error, I would say. Our error, I would say, is around plus or minus 3%. So this is with an experimental error breaking even, that first gas sample. We'll show later that this sample did not show any helium. A few days later, we got a large excess heat excursion up to about 26%. The ratio of heat out to heat in is about 1.26. And so that was on a weekend. The lab was actually rather cold. The room temperature is lower than normal, so I would say, if anything, this excess heat was probably really higher than this because of the cold air in the lab on the weekend. But this is where we took another gas sample, and this was the largest excess heat that we ever saw in the entire experiment. And this sample gave one of the largest amounts of helium that we ever saw. It was in this sample right here. We continued on, didn't get as much excess heat. We took another sample here and another sample here. And we did this from October into December. Now, before I go on any further, we need to talk a little bit about errors, possible errors in measuring excess heat. There's a lot of calorimetric error, and one of the major ones people bring up is recombination taking place, because we subtract the 1.53 volts. That is not valid if you have recombination. So you can theoretically calculate how much gas you should be generating at this current density, or current actually, 528 milliamps. And you go through a calculation. This is the Faraday's constant. This is the temperature correction. This is the pressure correction, even correct for the vapor pressure of water. And you get a theoretical value for a laboratory temperature of 6.73 milliliters per minute of gas that should be coming off. We measured this experimentally by the displacement of water. In cell A, we got 6.75 plus or minus 0.25. Cell B, we got 6.69 plus or minus 0.15. So with an experimental error, we were getting the expected amount of gas off, and again showing there's no recombination. But I give you quite a few other references of people who study this and come to the same conclusion. As long as you keep your electrodes submerged, you don't have recombination going on. So that error is not significant in this case. What about the heat effect when you load the palladium with deuterium? That does give off heat. That's the exothermic reaction as you load the palladium up with heat. But we don't normally do calorimetric measurements during the first day or so, because we know we're loading up the palladium and we know that effect is there. But even if you loaded it within an 8-hour period, how much power would that be of charging up the palladium in an 8-hour period? That would only be a minus 0.0253 watts, where we're usually working around 2 watts, so that's no more than around a 2% error anyway. But we normally don't even take calorimetric measurements that first day. What about the evaporation of D2O? Well, that's the opposite effect. That takes heat away. And we know how much evaporates because we measure how much D2O we add and how much D2O we have at the end, and we know how much evaporates. That's 0.19 cc's per day, and you can calculate the power associated with that. That's only 0.0054 watts. So neither one of these errors is very significant. In fact, they tend to cancel. One is positive, one is negative. So they tend to cancel each other out, and they are small besides. How does our excess heat measurement compare with other work? Here I'm comparing it with the Fleischmann and Pons work. They published in 1990. I drew the straight line because if you're above a certain current density, it seems that there is a linear effect. This is a log-log plot. This is the log of the current density on the x-axis, the log of the excess heat in watts per cubic centimeter palladium on the y-axis. Our data are the blue x's that you see there. But you see that for our current density, we fit in quite closely what Fleischmann and Pons report. And if you're above a certain threshold current, you need to be, if you're below about 100 milliamps, below this current right here, you see the Fleischmann and Pons results scatter quite a bit. They call that the threshold. You need to at least have a current density of 100 milliamps per square centimeter. But then beyond that, the excess heat tends to increase rather rapidly with the current density. Okay, you might then ask, what about the work of all these other people? Caltech, for example, that did not get excess heat. This is Nate Lewis's paper at Caltech. Well, Caltech is a very respectable place, and people believe anything published by Caltech is right. But if you study Nate Lewis's papers very closely, they have some very gross errors in them. I mean, he had a huge crew working on this. Look at all the co-authors. They did this very fast, within a matter of weeks, 6 to 8 weeks' work. That many people working that fast, they're bound to have made errors, and they did. But he claims that they had no excess enthalpy, and they did not see any helium production in their experiments, among other things. That's what I want to focus on. What was their detection limit for helium? From their own paper, their detection limit was 1 part per million. Part per million, not parts per billion. Well, you would not even expect to see helium at that low a sensitivity. The amount of helium coming off would be in the parts per billion range. In fact, from his current density and his electrode, I've calculated the most that he would have expected, based on the Fleischmann and Pons result, would have been 0.04 parts per million. Yet his detection limit is 1 part per million. It's no wonder he didn't see helium. His method is not sensitive enough. What about Nate Lewis's calorimetric data? He says he did not get excess heat. If you look at his heating coefficients, which I have circled here, this is his results in water. Now, a heating coefficient is just reciprocal of what I call the cell constant. If you want to call it degrees per watt, as he does, it's heating coefficient. If you want to call it watts per degree, then it's the cell constant, the way I use it. But you see in water, he was getting about 12.6, 13.1. The logical thing to do would be to calibrate in water, where you're sure of having no excess heat, and then using that cell constant. Because as I showed you in the previous graph, I've never seen any evidence that my cell constant changes over periods of months and years. My cell constant stays the same. Yet he has a lower value here for water than he has for heavy water. I already showed you that in heavy water, I got the same result as I got in light water. And note also, this is his electrolysis with time, 14.7 hours going on to 164 hours. Early on, he had a cell constant or a heating coefficient of 14. Later on, it was up to 15.9. That is a 14% change. Now, I could argue I don't have any excess heat either if I said my cell constant changes. See, his out is his cell constant changes. He says, there's no excess heat there. The only thing that happened is my cell constant changed. Well, anybody can say that. My results, I could say the same thing. But why does the cell constant change? He says maybe because of recombination, but we've shown that recombination doesn't occur. He said perhaps because of the rate and type of gas bubble evolution. But I've studied that. I've calibrated my cell at different current densities and different rates of gas bubbles, and I see no effect. So I think he really has an excess heat effect here. He should really use this constant early on, 14, and keep that constant the same. Then down here he has about 14% excess heat. So in his own paper he has evidence, at least I think there's evidence, that he had an excess heat effect. But he argues it away as a changing cell constant, but with no basis for that. I've written a letter to Nature regarding this, but Nature and a lot of other journals, they refuse to take up the cold fusion problems if you are attacking somebody that has a negative result. And so I don't think I'll get this published. But in addition to what I just pointed out, his method, he really cannot say whether or not he had excess power. All he can say is when he changed the electrolysis power, the excess power didn't change much as he changed the electrolysis power. He really cannot say from his, if you go through the algebra, he cannot say that he had no excess power. That's impossible to say by the method that he used. But the reason I want to bring up this Nate Lewis paper is I think that's a very critical paper. It turned the tide of public opinion against cold fusion. If you read it in Frank Close's book or Malice's book, you see that was a pivotal paper in changing public opinion against cold fusion, yet it is filled with major flaws. And people that are trying to get patents in this area, I've talked to people at SRI, their patents get turned down because of Nate Lewis's paper. So there are a large number of scientists now interested in cold fusion are trying to fight the Nate Lewis's paper because they are also a roadblock to getting patents. Well, continuing our work on, we never did see the large excess heat effects again, but we had a steady excess heat throughout the next time period. We were waiting for larger effects, but we finally took another gas sample here. We were also trying to measure neutrons by activation of metal foils. Indium foil, for example, can be activated if you have a neutron flux of 10 to the 4th neutrons per second. So we thought if we had that many neutrons, we could have activated the indium foil. So that's why we considered foil at that time period. We later tried gold foil because gold foil had a longer half-life when you activate it. It has half-life instead of an hour or two like indium. It has a half-life of 2.7 days. My brother's a nuclear engineer, so I could send the samples off to him, he had better equipment that he could see if any activation took place. He works at Rocky Flats in Colorado, and he had brought better equipment, so I used gold foil and shipped it off to him. These were good experiments, but we never did see any gold foil activation, so all we can say is the neutrons in our experiments had to be less than 10 to the 4th neutrons per second. In fact, Fleischmann and Pons now claim their neutron rate was not really 4,000 neutrons per second, but more like 50 neutrons per second, much lower. So this effect is basically aneutronic. There is not a lot of neutrons associated with it, whatever the effect is. Okay, one other view graph here. We took the lead foil out. We took the gold foil out here. We took another gas sample here. But the important thing I want to point out, at the very end of this experiment in December, we put in dental film just to see whether there's any radiation. There's a rough test for any radiation. We put it in here, took it out about a week later when we turned the cell off, discontinued the experiment on Christmas Day in 1990. Because I was kind of surprised when I got the results back from the dental film. This is a film in cell A, and it was totally exposed. The only reason there are some light spots in there is because the film got a little waterlogged. It was outside the cell, but it was in this outer water jacket, and it got some water in it, and so the emulsion stuck. When they tried to peel it away, there was some peeling away of the emulsion. So you do have some light areas. I sent this back to the lab. Actually, my dentist is the one that gave me the film, and I sent it back to him to have it developed. So it was a trip to the dentist that led to this experiment, actually. But he developed the film, and he said this was totally exposed except for where it peeled away. Cell B, this film was further away from the palladium, and it was deeper in the cell. For the bottom part, any radiation that hit here would have had to gone through a little pedestal made out of Teflon the palladium sit upon. The palladium sat upon that pedestal, and it did not have a direct line. The radiation would not have had a direct line. It would have had to gone through some Teflon. But the top part got more exposed, the bottom part got less exposed. This was a control film that I went through the whole procedure, except it was just sitting in water instead of near the electrolysis cell, and there's a little bit of exposure due to cosmic radiation. This is a fresh film with no exposure. This is a fresh film that's zapped with 70 kilovolts for 7 milliamps for half a second, just to show you what total exposure would look like. But anyway, something had to expose the film, and could not have been hydrogen because the film is outside the glass. It's not around the outside of the glass. Hydrogen would not have got into it. And we've done this many, many times since with cells that were not producing excess heat, and we have not seen film exposure. Okay, the gas samples that we collected at China Lake, California, we had to ship to Texas because our mass spec could not analyze for helium. It would only go down to mass 10, so that's why we collaborated with the University of Texas. And when they got the gas sample, they connected it to a chiral filter because it's very difficult to analyze for small traces of helium, mass 4, in the presence of large amounts of deuterium, which is also mass 4. There's a slight difference, but not much. So to really try to define in a huge quantity of deuterium gas, you have to try to separate the deuterium gas out first. And we did this by passing through a chiral filter, activated charcoal at liquid nitrogen temperature. We found one filter process was not enough. Some deuterium still got through, so we passed it through a second thinner filter, which really acted like a gas chromatography column. It slowed down the flow of any deuterium, so it got through slower. But by the time it passed through the second filter, then pretty much all the deuterium was removed, and only the helium was getting through. Then we would analyze for the helium. Because we were working at the maximum sensitivity of the spectrophotometer, there was always some hydrogen present, but this had nothing to do with our experiment. The chamber itself in the mass spec had some contamination from organic molecules or maybe from water. So such high sensitivities, you'd always see some peaks due to hydrogen. That had nothing to do with our results. But here you see the helium-4 peak, and if the deuterium got through, you could see the deuterium peak. But you could baseline separate these two peaks. You could actually baseline separate on this mass spec the helium-4 from the deuterium, as long as you didn't have too much deuterium. If there's any question whether it was really deuterium or helium, you could change the ionization voltage. Change the ionization voltage will shut down the deuterium peak, I think, before the, I forget, I didn't do this work, but anyway, it'll tell you the difference between whether it's helium-4 or deuterium by changing the ionization voltage. In fact, I think that's what we go into the next graph a little bit. You can resolve helium in the presence of deuterium. We reference the window to the hydrogen to Texas. The lowering in ionization voltage, what I was just mentioning, turns off the helium peak before the hydrogen species. Thus, you can differentiate, if there's any question, what is hydrogen, what is D2, and what is He. What is deuterium, what is helium. We never found helium-3, even though we were hoping to find helium-3 because that would have been a lot less controversial because it's not normally present to any appreciable amount in the air. Finding helium-4, you're always open to question. Maybe it got in from the air. But we didn't see helium-3. We found helium-4. Well, how much helium should we have expected? If you're getting 1 watt of excess power by this fusion reaction, assuming the energy, this normally gives off a gamma ray, but assuming the 23.5, I think it really should be 23.8 MeV. If that energy is given off to the lattice and appears as heat in the cell, how much helium would you expect? If it were a gamma ray, the gamma ray would escape the cell and you wouldn't see the excess heat effect. The gamma ray would carry it off. But so assuming that the energy stays in the cell, stays in the lattice, appears as heat in the cell, then 1 watt for this reaction corresponds to 2.66 times 10 to the 11th helium-4 atoms per second. That sounds like a huge amount. And number-wise, that is a large amount. But if you do a calculation, how long is it going to take you to produce 1 mole? Well, 1 mole is 6.02 times 10 to the 23rd atoms. It'll take you a lot of seconds to get 1 mole. In fact, it'll take you 73,000 years to get 1 mole. And so it's still not a lot of helium, even though it sounds like a big number. But anyway, 1 watt corresponds to 2.66 times 10 to the 11th helium-4 per second. This is the rate we're generating gas, getting 500, in 1 minute we generate 6.73 milliliters, and divide that into 500 is how many minutes it would take us to fill the flask, convert this into seconds, and then how many helium atoms we're getting per second. We weren't operating at 1 watt. The most we had was 0.46 watts. But anyway, theoretically, within that 500 milliliter flask, we should have had, based on our excess heat, 5.4 times 10 to the 14th helium atoms. So roughly 10 to the 14th is what you would expect theoretically. So this shows that theoretically we should have been producing about 10 to the 14th helium atoms in a 500 milliliter of gas sample. When we did the measurement, we came up with about 10 to the 14th, about the right order of magnitude. Now it was difficult to do this exactly quantitatively because there's gas kinetics involved in going through the Kyle filters, and so all we could say is that in some cases we had a very small peak, some cases we had a medium peak, some cases we had a large peak. Our detection limit was about 10 to the 12th, so we assigned that to the small peak. The medium peak we assigned about 10 to the 13th, and the large peak we assigned about 10 to the 14th. Now to do this right, we would have had to have deuterium oxygen mixtures with known amounts of helium. That had been the only way to really quantify it. But that's the best that we could do at the time, is say that we had either large amounts, medium amounts, or small amounts, which correspond to 10 to the 12th, 10 to the 13th, or 10 to the 14th. So within the order of magnitude is about all we can say, and within the order of magnitude, the amount of helium we found was about the right amount based on the amount of excess heat we were getting. And you can see that in the cells that produce an excess heat, we found helium. When the amount of excess heat was small, we usually found small helium, a small amount of helium. So there seemed to be also a relationship between how much heat we saw and how much helium we found. But in every case that we had excess heat, we found helium. In the one case where we had no excess heat, or with an experimental error, we did not find any helium. There were a couple of samples that we didn't know. The electrolyte level got too low on this sample, so we're not sure about the calorimetry. We didn't find any helium in that one sample. We show the sample, but we realize there's a calorimetric error there because the level got below the palladium. And whenever that happens, recombination becomes a very likely occurrence. And so that could very easily be an error. This one is probably okay. We put it down with it because they're both on the same day, but it was probably okay. The calorimetry, there's no reason to really throw that one out in that case. If you plot this, the amount of excess power versus the amount of helium atoms, you would like a nice straight line, but when all you can say is the order of magnitude, you can't expect a very good line. But basically, when we had low excess power, like down here, we had low amounts of helium. When we had large excess power over here, then we saw large amounts of helium. And that's about all we can say. We're trying to do this where we can quantify it much better. We've got a laboratory that can measure helium more accurately than we were able to do it, a commercial laboratory. And we're hoping to repeat this where we can get a much better linear relationship. And then that would also tell us what the energy of the reaction is, because the slope of this line would be equal to the energy of the reaction. Well, when we set up the experiment, we were planning on using heavy water cells that did not produce excess heat as controls. But most of the cells produced excess heat, and so we didn't have very many heavy water controls. So then we went to light water in January. We did the same experiment the same way, using the same cells. We used the same electrodes. We used the same gas lines, everything exactly what we did before, except we had water, H2O, light water instead of heavy water. And those samples were analyzed, and in none of these samples was any helium observed. So if you wanted to think about the possibility, here we have 5 experiments in light water with no helium and no excess heat. And we have 1 experiment in heavy water with no excess heat and no helium. So we have 6 experiments with no excess heat, no helium. We have 8 experiments with excess heat and helium. So we have a total of 14 experiments that turned out just right. With no excess heat, there was no helium. With excess heat, there was helium. What's the probability of getting this? It would be like flipping a coin and getting a certain sequence in 14 straight flips of the coins. If you want to write out a certain sequence and then try to flip a coin and get that, your probability is 1/2 to the 14th power. So the probability of that happening by chance is pretty small. So our best argument, this is one of our arguments against air getting in, is how did this happen by chance? This very slight possibility. Why did it happen in the way it did, if it's due to air getting into the system? We ran control experiments, no helium. We tested flasks by filling them with boil off nitrogen and shipping them back and forth to see whether any helium leaked in the process. As long as we shipped them by ground transport, there was no leakage. We had a couple of flasks that did leak when they were shipped by air. Because when you ship by air, there's large pressure changes, and that would maybe induce leakage. But we had to ship by ground because G2 and O2 is an explosive mixture. It wouldn't be legal to ship it by air, so we always had to ship the samples by ground transportation. The light water experiments that we ran in January, when we wrote the preliminary note, we thought we had some evidence for excess heat, but we found that was due to we were running experiments with dental film, and the liquid level in the gap was not where it should have been. But going back and recalculating that, we found that in the light water cells, we really didn't have excess heat either. Within our standard deviation, we were within break even on the light water cells. We did not get heat, we did not get dental film exposure, and we did not get any helium-4. I don't know whether I have enough time to go into this too much, but the major argument against our work is the possibility of helium diffusion through the glass. And that is a concern. Helium does diffuse through glass, but could it affect our experiments? You can calculate the rate of helium diffusion. It depends on the pressure of the helium, that's the partial pressure of helium in the atmosphere, and the thickness of the glass. And it could be a problem. It does diffuse through at a fast enough rate that it could be a problem. But experimentally, we correlated how long these flasks sat around after we disconnected them from our lines before they were analyzed for helium. Some sat for as long as 60 days and never showed any helium. And so if it was a steady diffusion of helium into the flask after we disconnected it, the longer the flask sat around, the more helium that should have diffused into it. So you should have seen a relationship. We see absolutely no relationship between how long our flasks sat in the laboratory before they were analyzed for helium. And this is evidence then that there was no appreciable diffusion affecting our results of helium from the air diffusion through the glass. In fact, the correlation for the detour results is actually a negative slope, not a positive slope. It's the opposite slope as what you would expect. It's not a very good slope at all, really, because the correlation coefficient is pretty bad. But if there is any correlation, it's in the wrong direction. Well, then how could you explain that it doesn't diffuse into glass? Well, one possible explanation is keep in mind you have 0.67, two-thirds of an atmosphere of deuterium inside the glass. It wants to come out. You have a lot more deuterium inside the flask than you have helium. Helium only exists in air at about 5 parts per million, the helium trying to go in. If you do a calculation, you have about 1,000 times more deuterium diffusing out than helium going in. Well, it is known that deuterium will displace helium from glass. They want to diffuse through the same places. They're both small molecules. They tend to diffuse through the same lattice sites. And so my argument is this huge amount of deuterium diffusing out of the flask tends to hinder or block helium trying to diffuse in. And that's why we did not see the effect of helium diffusion into the flask. There's a much greater outward diffusion of deuterium coming out, hinders helium diffusing in. We ran other cells. I want to point out, just in closing, that not every experiment gives us excess heat. In fact, we have many more experiments with heavy water where we do not get excess heat. This shows experiments in March and April and May where we had no excess heat in heavy water. So reproducibility remains a problem with these experiments. The Fleischmann-Pons type experiments with palladium rods, getting it to work every time is a major problem, and it's still a problem that exists. We'll skip that and just go to the summary. In summary, we found excess heat in these particular experiments in the palladium heavy water system. We saw heat at a maximum effect of 1.3 watts per cubic centimeter at 200 milliamps per square centimeter. We found helium-4 in the gases coming out of the cell that correlated to the right amount based on how much excess heat that we saw. We did not see any helium-3. That doesn't mean it wasn't there. It just means that with our detection limit, we were not able to see it. It could have been some there, but it was below our detection limit. Our detection limit is about 10 to the 12th atoms per 500 milliliters. So it still could have been there, but too little for us to detect. Our control experiments with light water showed no helium. And I think that concludes my talk. Thank you. Right, yeah, okay.
Here before long, and we have a plane to catch, but we do have time for a few questions. Is there any questions?
Excuse me, the electrode? Okay, palladium, the palladium? It was, we bought it from Johnson Matthey. It was 99.96 is what they quoted us. 99.96% palladium. Right. Yeah. Right. Yeah. Our anode was platinum rhodium alloy, about 20% rhodium. The reason we used that is that's what we had available. I have no really special reason, but it is true that impurities from the anode. We've done studies where we've seen some of the platinum and rhodium. They wind up on the palladium. The anode tends to oxidize, and you do get impurities that go from the anode to the cathode. That's true. Right here.
These results for power were in watts per cubic centimeter. Just order of magnitude, how many watts in and how many watts of excess heat were you seeing?
Okay. It would be about, a typical experiment would be about 4 watts in. But of course what usually is quoted was watts per cubic centimeter. Our volume was much less than 1 cubic centimeter, so the highest excess heat we saw in terms of water, excess power actually, was 0.52 watts, a little bit more than half a watt. That was the highest excess power we saw. Now, these are much smaller amounts than what Fleischmann-Pons have claimed in some of their experiments, but of course, we're working at much lower current densities. We cannot go up to the high current densities where they got their high power. You know, they reported values up to 10 or 100 watts per cubic centimeter, but they had to go up to very high current densities. We're not able to do that with our power supply because it overloads, so we had to stay within the working in the lower current regions, but where we're working correlates quite well with what they reported for the lower current densities, around 100 milliamps per square centimeter to 200 milliamps per square centimeter. But like you said, excess power, about 0.52 watts was the most that we saw. The input The input power could vary from 2 to 4 watts based on that. Now, in one case where we had about 25% excess heat, you could do a calculation of 0.52 watts. We had about 25% excess heat there. So that was input power is around 2 watts in that particular case.